Very good. Good afternoon, all of you. Thank you for coming, both in person and online. Today we have the second of our four speakers from outside the department. Today we have Dr. Ken Wacha, who's a research hydrologist in the USDA ARS building, National Lab for Ag and the Environment. His research focuses on quantifying and managing interactions between climate, soils, and land use, and their impact on hydrology and water quality at different scales, the field scale, landscape scale, and watershed scale. And you're doing that too. Process level work as well as watershed scale work. He's active in the long-term agro-ecosystem research, LTAR, that John Kovar has talked about in the past, and also the Conservation Effects Assessment Project, SEEP. These are both within ARS. Ken was born and raised on a farm in Northeast Iowa and received his BS and PhD in civil engineering and an MSc in geoinformatics from the University of Iowa. His doctoral research focused on landscape connectivity, rainfall and tillage erosion, and the redistribution of soil, carbon, and water across agricultural landscapes. Ken just started working with us.
This is correct. I mean, students can still have the old one.
September. Born and raised Iowa guy. We're very proud and happy to have him in our building, hopefully for many years to come. Okay, Ken, the floor is yours.
All right. Thanks, Dan. Appreciate it. Is that good for volume or blowing everybody out with speakers? All right. Title: Landscape Processes and the Role of Management in Building Resilience to Weather Changes. Should throw a couple more buzzwords in there. How, like sustainability? No, just kidding. I like this picture. This is a little snapshot here of some rainfall simulator work that we've done in the past. This is going to kind of highlight that upper surface of the soil that I'm going to talk about and how important it is, or how much I'd like to focus on that is kind of the active layer of the soil and the big interface between soil, water, and gas exchanges, and how ramping up intensification of weather patterns or management is really at the heart of impacting that. One more time. There we go. So I'm going to hit a couple challenges, go over some research that I'm working on, and a little bit of a vision for what I think is important about this. So no surprise, we're in the Midwest here. We got some productive farmland here. We're boxed in over there. Iowa is dark green. That means lots of corn production. These are prairie-derived soils. You know, you can throw about anything in the ground to grow them. The plot there on the left-hand side is showing Midwest corn grain production. And what we see, we're going along, and then 1945, we see a huge, sharp increase in production. And you know, genetic improvements and so forth, but intensification has really ramped up as well. And looking at that map, and if you look at a map across the US, you know, I've heard it said that the climate dictates the type and location of the crops grown. And then your weather is going to tell you how much you're going to actually get out of those crops that you're planting. So whenever you have this large increase here, that stair step, you're going to have intensification. You're going to have some intensification from management. You're going to have intensification from just trying to get as much out of the system as you can. And you can have years of big up and downs, yield gaps. It could be climate induced. It could be a variety of factors that are causing that. So in terms of like weather resilience, and I'm going to kind of focus on rainfall intensity. So what we see is in this top picture here, we're getting more rainfall, but it's not coming like if you had a bucket out there in the whole year, and you know, from year to year, maybe it's not going to be that much different. The problem is that it's coming at a more intense rate. So we see this, and I drive from Huxley to Ames here, and I get to see a lot of these little ponds out in the fields, you know, just sharp downpours. And yeah, kind of like this picture here. So more rainfall, less amount of time. It's not allowing it to get into the soil. And the other impact there is the impact of raindrop energy being transferred. So higher intensity rainfall is going to have much more energy being transferring the soil from those falling raindrops there. It can have impacts on sealing, crusting, and impacts of impacting the soil water exchanges within the soil upper surface. So knowing that that can happen at a field, how can this propagate to larger impacts within a whole drainage network watershed system? So one thing that I've been looking is that upper surface. So soil active layer, I would define that the top 5-10 centimeters. And soils within there, you can have low biological activity or high biological activity. So the one on the left, we don't want that. One on the right, we do. So management practices and different things that we could do to the soil to be able to promote that, your microbial community within there, you want to provide foods, shelter, in a stable place for them to be. Rain coming down at this intense ones here, you can have your aggregate structure within there collapse. You can have rupturing of pore spaces and clogging. It can, start to restrict your infiltration rates, and that can form a restrictive layer within that soil. You're promoting high biological activity, stronger aggregates. They're being held there. They're able to retain their shape and their structure within the soil to promote more water going down into the ground. I like this little scan here. So I wish it was just marbles and water being able to, from an engineering look from me, everything's a finite element, everything's structural. There's no deformable bodies in there. But in reality, the pore network is not this little marble, in there. So the Center of Non-Destructive Technology I worked out with a couple years back there, and I was interested in scanning the soil and looking at those pore networks. And if you imagine just like a little PVC little collection of that top surface there, and this is a scan going down, and it's just looking through there, and you're looking at the pore networks in there, and maybe you see some organic matter, preferential flow paths. This is coming from the side view, so you're going through the PVC there, and now you're kind of into the soil. And if you take a look at this, is this kind of sliver here of trying to characterize pore networks. I was interested at that time of looking into 3D printing, and now that's kind of evolved into like you can print them with like actual soil like material in there to be able to reconstruct that in hopes of intense tilled soils. Okay, here's your network of the pores, and you could just show that, as a prop almost, pour water through it. You could, look at different flow velocities and so forth compared to, say, I'm in a prairie here, the structures. I think would be a great informative one there. So that upper surface, now let's look at, now we're in like a hill slope kind of a landscape here. So when water comes down, basically the shape of that landscape is going to direct where the water's going. And there's a lot of processes, landscape processes that are occurring here. So you see some of these arrows kind of highlighting it there. You have concentrated flows start to develop. You got rills, gullies forming. You got lateral contributions of not only water, organic material, soil particles start to become detached and redistributed along the downslope there. What this does is it induces a lot of heterogeneity within that landscape. So if I was going to look at that landscape and say, moisture, all of these biological kind of drivers for when we're trying to model or predict what, this field here, what's the soil health of it, there's so much variability and so much transfers going in there that it's highly dynamic. Your respiration rates are from top to bottom are, highly variable. The soil types, just from long-term redistribution of material up and along there from eroding to depositional zone, is highly dynamic and, lots of heterogeneous impacts there as well. This was an event, I think 2013. So a big rainfall event here. This was a bunch of corn residue that the farmer thought was a good thing there. That hard downpour of rain, sealed surface, just basically like a parking lot, all that material transferred along here. This is almost 1/2 meter deep at the outlet there. So just thinking about trying to go in and plow that back into the ground, or, you know. So that's field, you know, so we started looking at kind of that soil column, and now looking at a hill slope and looking at this. But what would happen like if you're looking at a system? So this is a small little drainage basin, or like a little small watershed here. And now you got a collection of all these little fields, and based on management, they can become like a restrictive or a regulator of material going in or out. So high intense rainfalls, practices that are promoting, you know, strong aggregation and strong, or, you know, residue covers and stuff like this that can dissipate that rainfall energy. You allow the water to go in the ground. So there's a certain system on in balance versus out of balance. You start getting a restricted layer, everything, like I said, becomes like concrete almost, and it becomes just transported out there. This is the outlet here. 2009, this is over by Iowa City there. We had the big rainfall, but this was just this was an event that wasn't like a very famous one, but it was affected in this area. And a lot of it was because of this overwhelmed drainage network there that just became super flashy and just overwhelmed the whole system. So going back to the term soilscape here, this is what I did on my dissertation, was looking, I think about soilscape, and there's probably enough people in this department that can correct me on it. I think of a soilscape as, but a homogeneous unit of land. So like if I was going to say, this is all the same within this area. So by taking that approach, you do not account for any kind of a transfer into that system or into that soilscape or without of it. So if you take a field like this, you know, this is kind of that soilscape homogeneous one. You got litter incorporation, you got decomposition happening within that, and everything's pretty much vertical driven for processes. Now, if I look at this field here, I see some flow paths going on there. It seems like a pretty dynamic landscape there. So in reality, it's a collection of a bunch of soilscapes. And you see that there's a lot of transfer between basically node to node there to be able to connect those and to be able to update those. So what's needed is a collection of soilscape approach to be able to provide that connectivity to be able to get your lateral processes, to be able to connect and update, to be able to biogeochemical modeling, or, you know, whatever your interests are for carbon budgets. That's kind of that's where that needs to go, is towards a more landscape oriented approach. So some areas that I'm researching or have researched, kinetic energy of raindrops. So looking at that intensification, what's the effects of a small drizzle rain to, you know, what we see now is large amounts coming in a very short amount of time. This picture, I think, is really great, showing that scale. You got to remember that the aggregate scale is, you know, a couple millimeters down, or, you know, a millimeter down to sub that, and then raindrops. And there's a big collection of different raindrop sizes that fall based on a rain event. And those fall at different speeds. Some can hit 20 miles an hour when they're hitting the ground at the terminal velocity. Now add in wind, add in downpour, you know, that energy is much more intense. This was some work I did on trying to find a way to quantify the kinetic energy. So traditionally, disdrometers is kind of being used as a technique to be able to capture and freeze in the air with like lasers the distribution of raindrops within a block of a void of air, or a volume of air. So this one here is called the helicopter rain gauge. It's good if you walk in it for like a shin buster too, but you know, if you have one rain gauge, great, but why not have a bunch of them, you know, connected to a rain, or basically a flat bar that spins around like this. So the concept is this one here in the middle, that's basically going to get all of the rainfall that's coming. And as you move out, if you remember playing on the playground and your little, what am I thinking of? Merry-go-round. And, you know, it's fine when you're in the middle, but as you're the one that gets out towards the end, you know, that velocity becomes much more. So the concept there is that as that moves out further away from the center, your velocity increases. And as it increases into a point where you're capturing raindrops falling at certain velocities within those different bins, all the way out till there's none. So as this will spin, you're able to capture the rain, which has a mass to it. So the drop's mass, and you can relate that to the velocity. It gives you the kinetic energy equation for being able to calculate the energy. So you get a really neat little distribution with a variety of different rainfalls. And what I've done with this is it's helped me to calibrate my rainfall simulators that I've made. We have a neat unit down in our NLA basement down there, a setup for testing aggregates, and it's a little like a 1 square meter unit that can ramp up, I think, to 32 different rainfall intensities. This has also been a little project we did looking out at natural rainfall to see and make sure that the distribution of those energies. The whole thought is I want to be able to provide a standardized testing of a force upon aggregates that's reflective of what's going on in the field. So here's a look kind of at the setup in our basement. Sounds dark and dreary in our rainfall simulator lab. But I like this picture. We had this lady come in. Yeah, Catherine Gamble was taking some pictures back then for Jerry Hatfield, professional photographer, and she was able to capture some really neat raindrops coming down, and as it hits the soil and looking at that terminal impact there. What you see is it sits upon the top of a sieve there, and when you rain on it, I was trying to isolate certain size aggregate fractions, expose them to a rainfall for a duration of time, and collect that material as it's breaking down over time and be able to get a time series of that material. The whole thought there is conceptually, if you look there, there's like a phase 1, it's just direct impact from the raindrops as it's coming down and pounding into the aggregates. But then water starts to come in and you start getting overcome with those internal pressures due to the water forces overcoming that. They can cause them to rupture and slake. So one thing to look here, this is an example of 2 different spots in the field that I've collected the soil. I basically isolated the 4 millimeter down to 0.25, looking at the aggregate fractions there, and then how they broke down in time. So this axis here is in minutes there, and then percent remaining. So you're starting at 100 and looking how each of those break down. And the whole thought is now go back to that marble kind of a schematic. There is, you have this network of pore spaces in there. How will that break down? Is there a characteristic diameter that will be called clogging, or would be prompt to there? So this work here, I'm just putting it out now, is this concept of time to clogging based on that breakdown within the soil column there, to be able to give us insight into what would be happening in a field. Does this, think of it as now you're applying it here. What would be the response at the landscape scale if you had enough, like a soil grid? So this here has more carbon than this one, high carbon, low carbon, much more resilient. A lot of those fractions stayed kind of intact. This is after 20 minutes of rainfall. And then interesting to note, this is like your water stable ags here, and this is infiltration. This low one here, lower end here, more infiltration, more stable ags, just to kind of confirm that or affirm that. Then going out and looking at collecting some of these aggregates at different slopes and different positions of the landscape here. I'll put it, there's a lot of dots on there. Let's focus on this top one over here with roughly that 5% slope. So this axis here is slope here on the Y, and this is how much carbon is within the aggregates. And that circle there, that'll represent, like if I just took a sample in and I want to run CN analysis on a whatever machine. That's the number that's going to spit back for processing it. Now, what happens is this, your soil actually gets broken into these different size fractions here. And then I looked inside of them to see what's the carbon content within each of those. So high variability across there within that bulk. Does that provide the support for why are some of these aggregate fractions, stronger? What's making them stronger and so forth. But what was found there was slope had a very big impact on kind of the natural tendencies, showing that landscape of, impacts of the different processes over time are shaping those. This figure here is looking at some rainfall simulator work that I've done. And this all came about over time of performing rainfall simulations and looking at some of that material, that sediment coming out, and learning that, it comes in aggregate fractions are being transported along there. The traditional models were always showing it's all primary particles that are being redistributed, from here to here, and that's how they could track it. It's, just kind of a mass balance within that of this non-ending supply from a parent layer, providing it there, and this being moved. However, in reality, what I was seeing was there's lots of aggregates within there, different size ones. And when I went to go look and test into like what was inside of them, that's why I found they were holding on to so much carbon within there. And if you was doing like a carbon balance underneath and neglect those, your uncertainty just goes through the roof. In reality, you're removing a lot more carbon from a certain rainstorm. So these, I would call these the enrichment ratio experiments. And what we have for a plot setup there is 3 different rainfall simulators. We would go around to different fields of different management and evaluate what are the fluxes of sediment and runoff coming off of them. And this is our weir here, where we have kind of a continuous flow depth measurements. Here's this kind of a look, seeing the different fractions moving within there. And kind of an example here of some data here. So this is runoff coefficient. That basically means what's the fraction of it running off compared to what's being applied from rainfall. So if you had a perfect value of 1, it'd mean every drop's coming down is basically in runoff form. Whereas 0 would be, it's all going into the ground and not transporting. So as we're collecting this here, at each point along here, we'd collect the sample and do an analysis on the sediment and look into the real characteristics of what's inside the sediment and so forth. But for time series there. So in terms of flow, you can look and you can see these different management and how the different management practices or provide different forms of resistance here. So this one here is like a contour ridge. So it's got a series of steps and pools. Here you can see it kind of outlined a little bit better. So rain accumulates and kind of builds up, and then it'll rupture through and propagate to the next there, but it forms high oriented roughness against the your flow patterns. And then just what's the effects of residue management there? How does the flow networks go through there? We use a sequence of dyes to be able to track that. And then by using some of those, we've looked into like these different forms of erosion or different mechanisms here, spillover or head cutting. You start to see that being a driver of propagation back for transport. And then you have deposition within those contours and ridge. So the material comes in, settles down, bursts. It's very episodic. So the whole thing is that going back to try to improve and build upon some of these transport models is that, they're built on, this is a uniform slope and you have an unending supply. And the reality, if we're going to move towards knowing if these practices can work, we need to capture the real physics behind the water and movement and sediment as well. So for data wise, again, we can look at, I would isolate for clay, for how much is in the sediment versus what is in the, what's the content of the clay within the sediment, what's the content within the original soil. This can form I think that's kind of cut off on the top there, sorry. Basically enriched. So if I took a little soil sample and looked at the characteristics before this rainfall event, and then I collect my sediment moving out of the field, and you compare those two, there's a ratio that's called the enrichment ratio. So the sediment over the characteristics of the original soil. So you can do that with clay enrichment or carbon, nitrogen. And what we found here was by taking that sediment and looking very detailed into the specific surface area characteristics of that sediment, we were able to relate that directly to the carbon content of that, with the whole idea that finer particles adhere more carbon, or they can basically stick to them. So this kind of shows this a summary of a line here with the kind of a 1-to-1 ratio. Some of the outliers there were shown to be some of the aggregate fractions that, yes, once you start accounting for them, that probably goes away. So there is a definite need to be able to include aggregates, and within that, to be able to make more accurate predictions there. This whole thing, we go to build this modeling framework. And this kind of goes back to that picture of all those little, that gridded nodes, but looking at, you could break this up into a infinite number of little soulscapes, basically, and it's representing that transport there. The whole thing is to be able to update this active layer of what fractions are moving, what are depositing, or what kind of hydrologic processes are, shaping that along the surface due to different forms of roughness, and there are different critical versus subcritical flows over, say, residue, or over the ridges, or whatever would be the shape of the topography there. And all of that comes in and can be tied in with the biogeochemical model. Here we use, actually it was the day-cent model. Essentially it's like a monthly time step one. But basically we took that and we made it into a very detailed biological weapon that had the capabilities to show updates of erosion and deposition and stuff coming in there, and then updating that and to be able to change your crop production, it would change your respiration and so forth. So it would be a more kind of a realistic shape of what's happening with your carbon and nitrogen cycling. This is a site I got with the LTAR network, the long-term ag setup there. This is in Hamilton County. And what you see is this kind of a progression of the management here. So same field, 1930s, 50s, all the way to 2013. I want you to kind of take note, of the different blocks. Look at this, almost looks like little plots there from, some of the stuff. Or small as it, or the farms have progressed into this now. Kind of everything's planted the same just for ease. But what's interesting to note is there's a network, a flow network within here. So showing kind of the old legacy of the how it transports water, how it transports nutrients, and so forth. So this is a site we went out and do some gridded sampling to be able to take a look at what I was talking, the aggregates within that surface, and to be able to do some infiltration work, and to be able to look at kind of the characteristics of them each. And the whole hope there is to look at that landscape, and with the dense grid, you could say if differences in infiltration, or kind of how that would respond. So that if you put like this theoretical layer of water atop it, you could almost push it into it, right? Based on infiltrations and those capabilities of stability. And you can see where your runoff would develop within different spots in that field, to be able to almost do like a reconstruction, or a theoretical reconstruction of the long-term dynamics of the slope-driven topography of shaping that. So here again, that's kind of that network. These aren't exact little arrows there. I think Bradley could probably do better with some geospatial techniques there. But this is looking at that south field. So there's a natural flow from this bottom right up to here and through here. So this site's kind of unique. In 2016, it was under conventional management for like the last 70 years. And now we're in a reduced kind of a strip till with cover crops. And I want to see, how that landscape responds at that. So what we're seeing here, looking at the microbial biomass, that's kind of my indicator of how stable that is for the microclimate. It's also reflective of kind of your aggregates and aggregation. So within the first 2 years of going to that, we increased 150 milligrams per kilogram within those first 2 years. This is the grain yield here showing just in those two. This became, I thought that was interesting because it started to look more homogeneous. So here there was almost some kind of a landscape kind of impact, or, you can see the shape of it. And here we're looking at microbial biomass. pretty homogeneous looking, which is reflective of probably intensive tillage, that everything's kind of the same. But now getting away from that, those long-term kind of feedbacks and kind of the legacy effects of that network of there is kind of shown of this here. Aggregate stability overall for a field, 10% within those first 2 years. And wet mean diameter, kind of looking at that whole concept I was saying about that clogging, time to clogging. So in conclusion here, as I'm looking at the time. Oh, that one's fast. I was hammering it. Hold on. What time is it then? 4:40. Okay. All right. I got a little more to say then. So just coming back now, we just got done with the sampling effort where we went out again and we did the deep core analysis. And then now we went out and did this, sampled the same grid. And I think between this time step here, now we have several years. I think it'll be, yeah, this will be the 7th, planning into the 8th year of the conversion to this here. And we just actually got the results back on the microbial biomass. And since start to finish, it is doubled, like for the field wise. So much more activity. And right now we're just getting ready to do our aggregates. I'm excited about jumping in and seeing how that has improved there. Maybe that wasn't such longer there. So in conclusion, maybe we'll have some great questions. Anyway, landscape processes are shaping your fields basically. So we need to move from that soilscape thinking towards a landscape oriented approach to be able to characterize the system or, you know, what's going on so that we can actually uncover some factors that different management practices are actually causing to actually break up and improve, whether it's, you know, killing the energy that raindrops from surface cover, whether it's adding oriented roughness in the planting directions to be able to break up the conductivity of the flow and just give you more time to allow that water to go in, or, you know, is it management practices and promoting fresh inputs through cover crops that are promoting aggregation and your microbial biomass. All of those things need to be thought of to be able to, you know, better think how we can evaluate these practices in a more mindful of a landscape vision. Soil active layer. Soil sampling is always done. What's your, you know, you look at a paper, it's 0 to 30 or, you know, 0 to 15 or, you know, something like that. A lot of 0 to 30. But, you know, is that really capturing, I've changed, I want to improve my management, you know, what's it doing in a short term? Here, you know, I'm seeing that that's quick. It's a quick turnaround within that first 2 years. And actually the first year was even an improvement, you know, within some of that work there as well. But that soil active layer, you know, if you consider that as that interface, it's an interface to the rain, it's an interface to the flow, and you treat that well and you try to promote it and build stronger, more resilient aggregates, then you're going to become more resilient to whatever comes your way. This can include even drought. You know, all that will be tied in with increased organic matter and stuff there that's known to have better water holding capacities. So then again, taking a look at the aggregate characteristics. The other part I didn't show on there was in terms of water stable ags, I also like to look at the dry ags. So this is kind of more of a wind erosion kind of a focus. And by taking just a scoop of soil and air dry soil and then putting it in like a series of sieves on like a shaker table and letting it kind of break apart into these different bins, that I found has been a great indicator of the level of tillage intensity. So, or, you know, how vulnerable they've used like certain fractions in the wind erosion community that, hey, this is probably what's going to be, you know, moving in certain wind storms and so forth. But I like to think that these aggregate characteristics is a quick tool or quick indicator for a lot of different things going on in your field. You can take a scoop of soil, take a look at what's that dry distribution. Okay, it's kind of like an X-ray of how intense has your management been. And then also look at the stability will give you that inference into, your infiltration or what would happen during rainfall events to be able to predict runoff points or susceptibility to that type of erosion too. And last but not least, the stable microclimate. So promoting in that active layer where most of your microbes are held there, promoting a nice structured spot for them. I don't think they like collapsed pore networks and getting flushed out of there and swept to the bottom of the hill, over time there. So promoting that space and more resilient aggregates to be able to allow that pore network where they can go in and out of there, will also dampen raindrop impact and allow more water to get in the ground. And that's it. I think I had an ending slide. No. Any questions? Yeah.
We have a good amount of time, almost 15 minutes really, so each of you should come up with one question, okay?
And those that are not looking at the clock on the wall that I was looking at and I kind of was hitting. Okay.
Those are actually just for me.
Okay.
Nothing's coming quite yet.
Okay, go in the room here then.
When those that's rainfall simulation is after harvest or something? That study you did, when and what time?
That one there, that was a spring.
Could you repeat?
Yes, thank you. Yep. So the question was, what time of the year did we perform those rainfall simulations from the beginning? That particular one was in the spring. We're trying to focus on basically in this type of area here, that kind of a early spring, May, June window is that period there where stuff's most active and vulnerable. That's where most of your rain's coming, kind of down there in that May range. You're looking at the distribution. So focusing there and then focus on what the cover and what management conditions would be at that point.
But another thought is that, what about suppose like and after the harvest when there is like ground cover is gone, because if you are thinking about the springtime, you have at least some moisture is there already, right? Because it is not totally bone dry.
Mhm.
But if you are thinking about like after harvest, like October, November, that time, if you have some rain, you think that there will be more erosion or more kind of impact that time as compared to the springtime?
Good point. Question is, what about considering fall and the impact of the harvest and residue management at that point to that? And yes, we've done both. I mean, I was just showing that study there, but yeah, and in terms of like soil sampling and collection, I like to collect after harvest as kind of that bookend when I would go look to collect any kind of a sample anyway, because I think it's reflective of that as well. But yeah, there it's more, I would say, residue layer. I mean, there's some other dynamics there that, be much different than what's left over what was sitting over the whole winter and, kind of decayed upon there. There's some challenges, and actually what we saw was not much happens. A lot of times with the, that heavy corn residue with on there, you're trying to rain on it and stuff. So those that have or promote that high surface cover then handled more almost like a grassland.
Okay.
Ken, Rick Cruz on this end. Very nice talk, nice graphics and understandable. You had some nice relationships between soil organic carbon and aggregate stability early in your talk. Were those aggregates with different organic matter contents the same textures, or particularly clay content across also organic matter content?
This was the plot you were showing. You're talking with slope versus aggregate carbon. Was that the?
You had one in which you had slope position where you collected aggregates with different organic matter contents, and prior to that, you also had another graph showing soil organic carbon versus degradation of the aggregate component.
Yep. Yeah, he's asking, the question is about. 1 second while I pull it up here. I think that one
Previous
got-
slide, I think, was the one.
That one there, yep. The question is about clay content within these, were they the same? We did the soil, texture there. Was not looked at for each of the individual fractions, it was just looked at in the terms of bulk. But the differences between, like, say, those two there, very close in clay content.
Thanks. If no one else is going to ask a question, I've got another one too. Excuse me. Next to last slide, I think you indicated that grain yields had increased 20 bushels per acre in those 2 years. How do you know
Yes.
that was due to management or soil change and not due to weather conditions?
I don't. The question was, can you guys hear that? Okay. So the grain yield going up 20%, was it due to the management, or was it, weather impacts? It's not, it's just, sometimes going around, like, the thought would be, it'd be nice to put a dollar amount, or like, hey, if you do this kind of a conservation practice, now you get more bushels per acre. It was just an observation, I would say, but yeah, weather definitely could have been an impact. If I had a little longer history of those maps, maybe I could go back and tell. I just, kind of started at that point, getting them.
Thanks.
Question about the active layer. And I wonder, do you see that as a term that can be very precisely defined with an upper boundary and a lower boundary? And if you do, how would you define those boundaries? Or is the active layer concept something that is so variable depending on management and type of soil and everything else, that all you can say is, well, the active layer is just at the surface? Did you see the question I'm asking?
Yeah. The question here is on the active layer, and if it's is it a fixed, is it a depth, or does it take into account from site to site, or different features within that, different managements, or terrains, can that be applicable through all of them?
Here's an example of what I'm thinking. I could imagine the active layer on a soil with no residue starting here, but then if there's residue in the soil, the active layer actually starts out here. You see what I mean?
Yeah, and I would probably bound that off.
Okay.
I mean, just for traditional, or like not traditional, I would say, but like they go, like a biogeochemical model, their guts of it are going to say, if you read into the code, it'll say like box A, box B, and then this above and below, this transfers to here. It's a great point you make. It's, I would probably cut it right at that surface. I mean, the other thing too, like horizons, you start getting into that, it's the same thing. Is that removed, or hopefully we don't have any management that's promoting that. No, I'm just kidding.
Well,
For more complexity.
okay, so I'll just ask one more follow-up.
Yeah.
Could you put a lower boundary? That would be a useful boundary for the experiments.
That's a great point. I need to think on it a little bit for that bottom. I mean, where you would start where you basically in my schematic, there would be the bottom of the 5, but what would be the factors that would shift that to that point almost?
Michael, what are your thoughts on that?
Well, I've looked at a lot of thin sections of surface horizons. And very often in cultivated fields, the upper 2 centimeters or so are going to be a jumble of macro and micro aggregates with a lot of pore space. But below that point, the bulk density changes down to about 5 centimeters or so. And then below that, the bulk density changes again, and the kinds of aggregates are different as well. And so I'm thinking that the active layer might just be that upper 2 centimeters or so, right at the very surface, that is really gonna respond to a typical rainfall intensity. On the other hand, if the rainfall intensity is variable, maybe if I have greater rainfall intensity, maybe my active layer will be thicker. So it'll be an interesting hypothesis to test, where
Yeah.
you could see a relationship between the thickness of the active layer and rainfall intensity.
Well, you know, analogous to that, like in sediment transport, there's a features thing called loose material, or, you know, stuff that is moved and deposited, you know, here, you know, at that here, that's more susceptible the next time to be quickly swept. So, I mean, it's a little, I mean, it's similar. And then another thought, just initially when you're saying that, is maybe there's a certain, if I had like a penetrometer, or, you know, or some kind of if there's a push down to a certain resistance, then maybe that's that indicator, or maybe ground penetrating rate. I just, you know, something to give that resistance to a certain.
I guess,
Interesting question.
Yeah.
I mean, I guess the active layer might depend upon what you're measuring, doesn't it? And as you've mentioned, Michael, it might depend on the thing impacting the soil. If it's a heavy rainfall or moderate long term,
Yeah.
you might need.
The active layer could also be defined by biological activity. You can say earthworm activity defines the active layer.
No, rooting
does.
Yeah.
Or rooting does.
Yep.
So that kind of goes back to my first point. Maybe the active layer is so variable that it's so fuzzy. Is it useful? That's what I'm wondering.
Or it might have a site-specific usefulness, you know.
Or they just increase it's between this and this. You know, that's kind of how it hasn't been properly defined, I guess. Yeah.
Laura?
Dr. Horton has a question, at least he's made his.
Thank you.
mind. Yes.
Great,
Yeah.
thank you. So I was going to ask something similar to Dr. Thompson. On your summary slide, on the second point of your summary slide, when you were talking about the active layer, you mentioned, a lot of people sample the soil for 30 centimeters, the top 30 centimeters, or maybe the top 15, but I didn't hear you say about the active layer, how thick or how you thought people should sample the soil, or how thick is that active layer. You didn't mention a number. What kind of number would you say for the active layer?
Here I was proposing 0 to 5 before Michael threw my whole world upside down.
Yeah, well, I wanted to say something about that too. It might be
it's a great point. It is.
Let me say something, okay? It might be serendipitous, if that's the right word, but we've done quite a bit of work on soil water evaporation. You're focusing on infiltration, runoff, but another component of the hydrologic cycle, evaporation. And we found in Iowa the water's evaporating from the surface when it's really wet, and then as the surface dries out, evaporation starts to occur in the subsurface. But we've only been able to measure the subsurface evaporation down to a depth of about 5 centimeters. So all of the evaporation is occurring in the 0 to 5 centimeter layer, surface layer of soil. So maybe it's a serendipitous thing. I hadn't heard those words, the active layer, before for hydrology, but maybe there's another little plug for it as well. Thank you.
Yeah, that's interesting. Was that for the Iowa ones? Was that soils around here, or was it like for the evaporation?
Yeah.
Okay.
Soils around here.
Any other questions online while we have more here yet in the room?
Nope, not seeing anything so far.
Okay, Amit, I think you had your hand up.
Well, I'm just wondering about, like your 75 meter by 75 meter grid. And did you do the texture for all those grids? Means how many grids you have for the area size? For 75 meter by 75?
How many samples in each?
Yeah,
Build-
how many
Say 60 in each. 60 samples
for each 75 meter by 75 meter?
at each grid point.
Oh,
I mean, there'd be 60 flags, you know.
Did you do the clay content or texture analysis? How variable that clay content is?
We did it on, when we did our initial deep cores. We did the texture analysis on all of those.
You did or you?
Did.
Okay. Did you see any variation in clay content?
There's variation along like those flow pathways. The question, I'm sorry, after anybody's listening, was about the sampling grid, the 75-meter grid on that field, and about variability of the clays and texture. But yes, it's, you know, some along the flow paths there. And that kind of a network I was showing the.
Why I'm telling that thing, because what I'm wondering that because you mentioned about a microbial biomass carbon, you have mentioned there is a change or something like that. I'm wondering that whether that differences is coming from the inherent differences in clay content or soil characteristics, or it is management. Means I think that is more like inherent soil characteristics, not that much contributed by the management or differences in management. But it's my thought that.
Which part the
For the microbial biomass carbon.
Oh, the microbial.
Contributing that, okay, management is changing the microbial biomass carbon. My question is that how you are going to do that part, whether it is a different difference of the soil or it is contributed by the management.
Well, that actual parameter I've measured 16, 17, 18, 19, and then now again in 23. It just step increases each year.
Okay.
And that was changing from conventional
Conventional.
tillage to strip till with a cover crop.
Yeah.
So it's a big management change there.
Yeah. And then the first round was when it was still in conventional. Kind of that baseline. And what was really seen was it was kind of there wasn't much variation amongst the different spots that were sampled, the grid. It was more, like I was saying, like, you know, the intensive tillage or whatever they were doing made it more homogeneous for the whole field or whatever conditions. And now there's starting to be some, if you look at your changes, it kind of is reflective of a lot of the flow network on that field, actually.
I have a question about regulation. I mean, do farmers in Iowa, are they subjected to any regulation that tries to minimize soil erosion? And if they are, or, you know, maybe planning through NRCS or whatever, if they are, how well does the current policy build on this soilscape view, or is it instead much more bigger scale?
You would have things like different BMPs, I mean, to put in, but nothing in terms of this management, you know, causes or the erosion. But I mean, you'd have implementation of like grass waterways, terraces, you know, things to break up runoff generation and, you know, for erosion, or some stuff maybe on some contours. I mean, that kind of a literature, but it's more blanketed, I guess, for.
Yeah, probably based on empirical observations.
Yeah.
But if you do these contours and
And then it's this field, it's designed by what is your slope, what is your slope length, you know, kind of how do you design it, what's the width need to be for whatever your projected runoff with based on your USLE method, kind of a formulation of more regional or kind of estimates or regional data.
okay, thanks.
Somebody may have direct messaged you a question.
Okay.
that I can see.
in the chat.
I am a good baseball player. My nephew is. Yep,
Okay.
my nephew, yeah, he pitches with he was with the Cardinals, yeah.
Oh, wow.
Now he's with the Padres, so.
Okay.
Anything
well,
else? Yep.
Yeah, we are over, past the time limit. So thank you all of you for coming, for your questions. We had a very good dialogue. Thanks to all of you online as well for joining us. We'll see you next week with another invited speaker from the outside. Thank you.
As you said that, I was like, uh-oh. If it wasn't, who's on this?
You can stop recording now if you don't want.
Okay.